Hello everyone, I'm Hendrik and I work as a C++ developer for the Rosen Group in Germany. And at work we use C++ 20 and all of the latest and greatest features of C++ as soon as they become available in GCC and Visual Studio. And this is really cool, and I think this is not the case for everybody who works with C++, and this is my motivation to tell you a little bit about the fancy new stuff I love so much about C++. And in C++ 20, there were a lot of improvements around templates, and this is a topic for today. So this talk has a lot of content, and hopefully everything will fit into the 90 minutes. And the talk has dedicated chapters, and at the end of each chapter, there's a slide which indicates that I will now do a little pause and answer your questions. You might want to follow this talk along by looking at the slides on your own laptop. There are several ways to do this. One way is to just type in the tiny URL here you see on the slide, so tinyurl.com/2p8dj5cr. Or if you are like watching this in the stream on Zoom, you can now pop out your mobile phone and scan the QR code. Or the track host was so nice and offered to put the tiny URL in the chat as well. And yeah, this should work out. On some slides, you will find links to Compiler Explorer for trying out code examples, and I will also show them during the talk. On my slides, I usually leave out most of the includes unless they are necessary to make a point, and you will find them, of course, in the working Compiler Explorer examples. Feedback and questions. So there are several ways to do this. If you're watching this on Zoom, you can put your questions in the Q&A system of Zoom at any time, and I will answer them during the talk at the indication slides I have for that I will now pause and answer questions. You can also put questions in the Discord channel for the SS Great Britain, and I will look in there as well at the time and answer questions as well. And I heard also that the people in the room can use the laptop or the microphone there and then ask questions. If this talk is over and you still want to talk to me, there are also two possibilities for that. After the talk, I will go to the SS Great Britain room in Gathertown and answer questions there. And if you still much later want to talk to me, you can just approach me there on the virtual platform or send me a DM on Discord. Or if you are interested in that, here are my socials for Twitter, LinkedIn, and GitHub. You can follow me there and ask me questions there as well. So before we start with the content, I want to recommend some other talks which have similar topics here. So on Wednesday, there was a talk, C++ 20 concepts from Andreas Fertig. And then C++ 20, my favorite code examples from Nikolai Yusutis. And later on today, there will be a talk by Cy Brandt, documentation in the era of concepts and ranges. And these are all, I would say, they live in the similarity of my talk, and I would recommend watching these, although the first two ones lie in the past now, and you either have watched them already or can still watch the recordings. Yeah. So, as I was thinking about templates and C++ 20, it came to my mind that a lot of things has happened, and I immediately thought about this classical quote from Monty Python's Life of Brian and made that my title for my talk, because I love Monty Python and the quotes from it, and they have huge meme potential. And I also took it because I think in C++ people always want more features in a new standard and are not satisfied by the amount they get with a new release. Yeah, and let's talk about it. What's in C++ 20 for templates? So concepts are by far the biggest template-related feature, and I will talk about them, I would say 50% of the talk time. But also the changes to non-type template parameters are really revolutionary as well and can be useful in a lot of places. Lambdas have been changed with the addition of templated lambdas and the possibility to use them with concepts. So a lot of stuff has happened, and I will try to go through everything. But of course, in 90 minutes, not everything can be discussed in detail. So let's start with concepts. This chapter will be about what concepts are and how we can use them in our code. So what is the use case for concepts? So we have a function or a class template in our code, but we want to limit what the template parameters can be. And this is, of course, already possible in C++ 17. We have tools like enable if, static asserts, which we can use enable if to steer a SVNA in some direction. We can use static asserts to just halt the compilation if we're not satisfied with the types. We can use type traits to find out what we put into a template. We can write our own type traits with tools like void t. Everything is still possible. But with C++ 20, we get concepts which improve on that in several kind of ways. So if we write concepts, the code that we get in the end is much more readable than everything there was before. We get also improved error messages, which tell us exactly what is wrong with our code and what we can do to fix it. And concepts and the associated type constraints also give us some rules on subsumption. So what happens if we have two things which are very similar, but one constraint is already contained in another one, which we will see later on in detail. And this is a really, really well-designed feature, which helps us a lot. Although in general, all the tools to achieve the same effect were already there in the past. And one warning, so concepts don't necessarily bring a compile time improvement. So I was asked this a lot in my previous talks. You can find on the internet, if you Google for concepts and compile time benchmarks, you will find several people who have tried that out and came basically to mixed results. Yeah, for some cases, working with enable if was faster. For some cases, concepts were faster, but this is not like concepts are not a feature to improve your compile time performance. So then let's dig in and have a look what a concept is. So concept is a compile time predicate on template parameters. So we have a compile time function which maps a template parameter to a bool. We can have a look here. For example, stood forward iterator of t is a concept, and if it's true, if t is a forward iterator. Another example would be stood constructible from with t and here variable template arguments args, which is true if t can be initialized with args. And this usually is used together with constraints, and constraints will limit what types a template function or class will accept as template parameters. With C++ 20, we get also concepts from the standard library, and they can be found usually in 3 headers. There is the new concepts header, which contains, I would say, already almost all the concepts you will need in your day-to-day work. There are things in there like checking if 2 types are the same, if one type is derived from another, if it's an integral type, a floating point type, and so on. So a lot of basic checks are already in there. If you want to have concepts which evolve around iterators, they can be found in the iterator header. And for ranges-related concepts, there's also the ranges header. And of course, third-party libraries will bring with them their own headers with concepts in them, possibly. So we will start here with the first code example by looking how we can use constraints on function templates. So to check the type requirement at compile time, we can use a constraint. So this is here highlighted in yellow on the slide. This is a so-called requires clause. which here appears as the last element of the function declarator. And we have a function, we have a concept here, which is stood floating point from the concepts header, which is true if the type T is a floating point type. And of course, these requires clauses can also be used for class templates, variable templates, or alias templates. But for simplicity, I show here only an example for a function template. So, and what this requires clause here will do is we have a norm function which takes a vector of type T and calculates something like a vector norm from linear algebra on it. And this only makes sense for floating point types like floats or doubles. So we put in here a type constraint which checks whether the type T is a floating point. This is the motivation for doing that. And this tells us as user of the code in a very readable fashion what the function should accept, the function template should accept. And if we violate that requirement, we get a short and nice and easy to understand error message. So how would error messages look like with concept? So it starts here with telling us that we have an unsatisfied constraint. If we put something in which is not a floating point type, for example, string, that tells us the expression is floating point v evaluated to false. So, okay, it checked whether something is a floating point and that evaluated to false. This is, I think, very understandable. And if you're not satisfied with the level of detail here, there's also compiler switch to increase the diagnostic depth here. But for this simple example, where the requires clause says, please give me a floating point, and I gave it a string, I think this is sufficient. If you have more complicated concepts which check a lot of things, then maybe you need to increase here the diagnostic depth. But for this simple example, this suffices. Then let's talk in detail about the requires clause. So the keyword requires is used to introduce a requires clause, which specifies constraints on template arguments here on the function declaration. So it can appear as the last element of a function declarator, or it can appear right after a template parameter list. And the keyword requires here must be followed by some constant expression. So it's possible, or so you're not required by the requires clause to use a concept here. You can use something else, for example, a type trait or some kind of const expr bool, or you could also write true or false if you want. But the intent is that most of the time you will use named concepts either from the standard library or maybe some named concepts you've come up with yourself. And you can, of course, also use logical combinations of concepts, like here in the third example, where the requires clause is followed by my concept of T and my other concept of T. And then both of these need to evaluate to true in order for the requirement or the constraint to be fulfilled. But maybe we want to change our norm function a little bit. So in the first example we had, it accepted like a vector of type T, but maybe we don't want to be limited by a vector. We want to accept it some kind of container which contains floats and then calculate the vector norm. And this we have here. So we have now a requires clause which has two parts which are combined with an and. And the first thing here I want you to look at is that we require that our type name T has an inner type const iterator, which by the concept here is checked to be a forward iterator. And we combine that with another concept, which checks whether T has an inner type value type, which is checked by a concept to be be a floating point type. And this works out and works well. It checks what we want. But here, if we put all that here in the function declaration, this is a rather lengthy read. And it's, if you see that in code, it would be, I guess, a large line, which you don't usually like. And it has a lot of logic in it. And maybe we should put it somewhere else and store it somewhere and use it here with a shorter name. And this is what creating our own concepts is about, so that we don't have to write out this complex code here, but can put it somewhere else and also reuse it. So how would we write our own concept? So here this slide says it all. We start with a template keyword, then a template parameter list, the concept keyword. We give our concept a name, and then this is followed by a constraint expression. And the interesting question here is, what is a constraint expression? So constraint expression is the combination of other concepts and compile time Booleans and or requires expressions. And we will learn later on what requires expressions are. So here in this example of the slide, we have a template type name T concept. We call it my concept, and it's equal to other concept of T or a type trait. So stud is integral T value. This is an example for something we could do to write our own concept here. And with writing our own concepts, there are usually only two things we are not allowed to do, which I would call pitfalls. So one is concepts cannot recursively refer to themselves. So here in this example, I have a concept recursion, which refers to itself. This is not allowed. And the second thing is concepts cannot be constrained by a requires clause. So here I have a concept C2, which is something just indicated by 3 dots here, because it's not really important what would be there. But we try to constrain it with a requires clause. We would say concept C2 is constrained by the fact that it needs to fulfill concept C1 of T. And this is not legal C++, this is not allowed, and also it's not necessary. We can achieve the same effect by just combining these concepts with an AND. So we could write concept C2 is C1 of T and whatever is written here in the 3 dots. So we don't need a syntax like that, and that is a way, or that is one of the reasons why this is not allowed. So the next thing I want to talk about when creating our own concepts are requires expressions. So the keyword requires can have 2 meanings in C++. We have already seen the requires clause, which is used for a constraint, but we have also requires expressions. And a requires expression is an expression of type bool. Thus, that describes constraints on some template arguments. And we have the following syntax here. We have requires, then an optional parameter list, and then a requirements sequence. So the parameter list is a comma-separated list of parameters, like you have usually in a function declaration, except that default arguments are not allowed and it cannot end with an ellipsis. And these parameters have in general no storage, linkage, or lifetime, and they are only used in specifying requirements. And these parameters are in scope until the closing curly braces of the requirement sequence. And the requirement sequence is aptly named a sequence of requirements. Each requirement ends with a semicolon. There are 4 types of requirements, which we will talk about in detail. There are simple requirements, type requirements, compound requirements, and nested requirements, all which do these checks in a slightly different way. And these requirements may refer to the template parameters that are in scope, local parameters introduced in the parameter list, and to any other declarations that are visible from the enclosing context. And what happens in this requirement sequence is that the substitution of template arguments into this requires expression may result in the formation of invalid types or expressions in the requirements or violation of semantic constraints of these requirements. And in these cases, the requires expression will evaluate to false and does not cause a program to be ill-formed. And if substitution and semantic checking succeeds, the requires expression will evaluate to true. So, and to get to the bottom of that, I think an example is helpful. And on this slide, we have an example for a so-called simple requirement. And a simple requirement is an arbitrary expression statement that does not start with the keyword requires and is checked whether the expression is valid. The expression is an unevaluated operand in the sense that only language correctness is checked. So what have we here? We have the requires, which starts the requires expression. We have an optional parameter list, which defines two parameters, A and B, which are used for checking something later in the requirements sequence. And here we have the simple requirement A plus B. And this translates, or the meaning of this requirements, or this requirement in this requirement sequence translates basically to what is written here in the comment. So it is checked here whether the expression A plus B is a valid expression for the type T and will compile. And this forms the concept, which is therefore called edible. So if we have a concept edible with this requires expression consisting of only this simple requirement here, it will just check whether for type T, two parameters of this type T can be added without problems. So it will work for ints, floats, doubles, whatever, but not, I don't know, for some empty struct X, which you define. And of course, edible is not a very good concept, but it fits easily on a slide and can be easily explained here. Next thing are type requirements. And a type requirement is started by the keyword type name followed by a type name, which is optionally qualified. And the requirement is that the name type is valid. So it can be used to verify that a certain nested type exists. So here we have the concept has nested types, and it has two type requirements, and it checks whether the type T has a nested type value type and the type T has a nested type size type. And if both of these things are true, then the concept has nested types for type T will evaluate to true. And if one of these or both of them do not exist, then the concept has nested types will evaluate to false. So the next thing would be compound requirements. They look a lot like the simple requirements, but have a little bit more functionality. So again, we have an expression, which is now here in curly braces. Then we have an optional no except specifier, and we have an optional return type requirement. And the return type requirement needs to be a type constraint. So for example, a concept. And what is the meaning of that? It's really similar to what we have seen with the simple requirement. So at first it is checked that A plus B is semantically correct or valid C++ for the type T. And because we have here the optional no except qualifier, this expression is also not allowed to throw. And with the return type requirement, we check whether the result is convertible to float in the end. And if all of these three facts are true, so A plus B is valid C++ for type T, it cannot throw, and with the result is convertible to floats, then this aptly named concept edible like floats will evaluate to true. And yeah, if one of these three things, or two of them, or all of them are not fulfilled, then this concept edible like floats will evaluate to false. Yeah, and then the last type for requirements in the requirement sequence is so-called nested requirement. And this starts again with the requires keyword followed by a constraint expression. So this gives us the possibility to put constraint expressions as part of the requirement sequence. And this gives us, for example, the possibility to use concepts in here. And yeah, nothing more to say about that, basically. But now coming back to the example from the beginning. So we had this norm function with a really long requires clause, and we wanted to get rid of this real long requires clause and put that into our own concept. So now we've had a look how these concepts work and can basically do that. And what we here just do is that we can define here our own concept by combining existing ones from the standard library, just as we have done before in the requires clause. We now define our concept iterable with floats, which is just what we have written in the requires clause before. We check whether T has a nested type const iterator, which needs to be a forward iterator, and we check whether T has a nested type value type, which needs to be a floating point type, and call this our concept iterable with floats. And now we can insert that into our requires clause. So how would that look like? Again, like before, but now we have a just much shorter requires clause, which is much more readable, and we can reuse this iterable with float concepts anywhere else in the code if we expose it via a header file, for example. There's an even shorter way to write it if we want to. So instead of writing template type name T and then have the requires clause, we can just write the name of the concept here in the template parameter list and write template iterable with floats T. And this is, at least in my opinion, a very handy shorthand notation for using a concept in a constraint. And if we have concepts which only have one template parameter, this is easily done and I think very much readable. But my personal suggestion, and this is just a matter of taste, and I will be perfectly fine with you if you disagree with that, is that I would use requires clauses for concepts with more than one template parameter to avoid misunderstandings. Because if you have a concept which accepts several template parameters, you need to remember which one of these template parameters gets filled automatically. And here, so iterable with floats has just one template parameter, which gets automatically filled with T here. But if we have something like we've seen in the beginning, stood constructible from, then we need to remember, okay, which one gets automatically filled by the syntax? Okay, we can look it up. It's the leftmost one. Okay, we can remember that. But also, if we get more of these angle braces in here, if we have concepts with more than one template parameter and we need to fill out the rest of them here, this can start to look ugly because we have more of these angle braces in here. But again, this is just my personal opinion, and I'm totally fine if you want to write everything with this shorthand notation and not only concepts which just have one template parameter. So next example, or is an example where I think concepts can be helpful in the real world. So I call this example a function which takes another callable. And here we have a call twice function. and it takes a callable via a template parameter. And this is usually the way we pass on callables to functions in C++. And yeah, we also give the call twice function an int as an argument and then just return the sum of this callable. And this works out well, but without any documentation or concepts, the user might not be clear what the callable is expected to be by the call twice function. So what does the callable accept as parameters and what should it return? So by looking at the function declaration, we maybe can guess that the callable should take an int as an argument. And by looking at the return type of the call twice function, we might also guess that it should return an int, but we cannot be sure. So we have to look at the function body to really understand that of the call twice function. And here's a thing where concepts could help us to make that more visible and also to check that. And again, there are also things in C++ to do that before concepts. So there was std function. If we would use std function here, it would also clearly express our intent what callable should be. It should be a function which takes an int and returns an int, but usually in most of the cases in real world code, we don't use std function because it has a runtime runtime overhead. And usually we want to have these things checked at compile time without any runtime overhead. So how could we do the same thing which std function achieves with concepts? And do we need to write our own things here, or can the standard concepts from the standard library help us? And the answer is we can do all of these things just with the standard concepts from the standard library. So if we have a look now at our call twice function again, it's again a template, function template with a callable. And now we have a requires clause, and we require a concept called func with std, which takes here the callable template parameter and 2 ints. This is our requires clause. And now we have to look at how this concept works. Here we have a concept with 3 template parameters, func, arg, and ret. And it consists of two parts. One is the std regular invocable concept, to which we give the func and the arg. And this checks whether func is a callable which can be called with arg and is regular as well. I don't want to explain what regular here is, but let's say it behaves like a normal function. And this is checked with std regular invocable. And if func can be called with arg, then std regular invocable will return true. And the second thing here is we have std invoke result t. So we get the result type, which we would get if we would call the function func with the argument arg. And we check with the std same as concept that this invocation result here is the same type as the return type ret. And we combine both of these concepts with the end. And this means that we have achieved basically the same functionality as std function has when we would just want to check whether the function signature of our template type callable here matches with what we expect. And of course, we could have written this also if we would write down the requires expressions and some requirements in the requirement sequence ourselves. But it's usually better if the standard library gives us the same functionality to do it with the standard library, because concepts from the standard library should be better designed than the things we can come up with in couple of minutes of thinking, because they know also some edge cases and have some other properties like subsumption, which we are interested in. Yeah. Then next thing would be concepts and auto. So in C++20, we are able to constrain auto. So we can use a constrained placeholder like a concept. In each place, we can use auto. So I can write here a function divide, which uses auto return types and auto function parameters. And I can constrain all of these with the stood floating point concept. And this is a nice shorthand notation. So if you want to think of that in terms of templates, usually that would mean that first and second and the return type are their own template parameters, and each of them is constrained by a stood floating point concept constraint. And this can also be very nice if you want to, if you like auto, then you can constrain it in your code as well. I usually like auto, so I like this kind of syntax, but I know it can be strange to look at in the first place. So next topic in terms of concepts would be overload resolution. So how does overload resolution work with templates in general? So the compiler starts looking at the most constrained version of a template and ends with the least constrained or unconstrained version of a template. And this means we do not need a negated concept in overload resolution. So for example, if you have a function which has some constraints, so some requires clause with some concept, and you have another function which does not have a requires clause, so it is unconstrained, and then you call that function with a template parameter which fulfills the constrained version, then the constrained version is called. And if it does not fulfill the constraint of the constrained version, the unconstrained function is called. So there's no need to write another function template which has like requires not concept of something. This is really cool. And we will see examples of that later. A named concept can restrict other named concepts via subsumption. So we have something like, can have something like concept B is concept A and something else. And this is also used in overload resolution and checked basically in the hierarchically where the overload fits. And the overload resolution will prefer a concept that subsumes another. This is hard to understand on slides, and I think this gets easier to understand if we look at code. And this is as one limit, though, these subsumption rules only work with named concepts and Boolean combination of concepts and not with other things like const expr rules or, for example, type traits. And the concepts of the standard library are carefully designed to use this, which is also why I earlier gave the remark that it's a good idea to use concepts from the standard library. And now let's have a look at what I meant with concept subsumption and try to explain there. So I will open up now Code and Compiler Explorer, and if it's not readable, I would like you to make yourself noticeable. Good. So now let's talk about this code here. We start here in line 10. We have a concept A with a compound requirement. And what we require is that our type T here, and parameter of that, has a get function. And this get function should return something which is a stood floating point. Then we have another concept B, which is, or which should fulfill the concept A of T, and also requires that our type T has a get special function, which also returns a stood floating point. And now we have two function templates print, and one is constrained with concept A, and one is constrained with concept B. And now if we look at that, we see that concept B is subsuming A, because concept B is A and something else. So it's more restrictive and it contains A. And what happens now if we call print with a struct, for example, or some other type in overload resolution, it will be checked whether it fulfills B first and then A. And if B is fulfilled, this will be used. And if only A is fulfilled, this will be used. And we can see that here I have a test struct, and our test struct has a get and a get special function. So what we expect to fulfill B. And when we call print with this test struct, we get in the output hello from B. So because it fulfills B, which is A and something else, this overload is chosen. And if I would go in here and comment out this get special function, and it will compile for an eternity, it seems. And then this overload here is chosen, and we get hello from A. So nice and easy, hopefully. So next example. Now, this code looks kind of similar to what we had before. Again, we have a concept A, which requires that our type T has a get function, which returns a std floating point. This is exactly what we had before. And now our concept B has a little bit larger requires sequence, 2 compound requirements instead of 1. And it checks whether T has this get function, which is a floating point, and T has a get special function, which is also a std floating point. And the only difference here is that we don't explicitly state that we want to have concept A and something else. We just re-implemented the functionality of concept A here. And this makes a rather large difference, because now we have broken overload resolution here. Because again, I have my struct test here with the get and the get special function. So it fulfills B, and it kind of fulfills A as well. And if you call print with our test struct here, the compilation fails. And we get here call of overloaded print is ambiguous, because now concept subsumption does not work anymore. Concept subsumption only works with named concepts. So in the last example, we had concept B is equal to concept A and something else. But now we have just re-implemented the functionality of concept A, and the compiler cannot figure out that this is a case where B is a more specialized version of A, which will break overload resolution here. Next example. Here again, we have a concept A. It again checks whether this get function is there and a floating point. And now we have a concept B, which only checks for this get special function. So now concept A and B are not related anymore. And now I have a function print, which again is constrained on A. And now I have a function print, a function template print, which checks via a requires clause whether A and B are fulfilled. And now concept subsumption works again. Yeah? We have A and B. This is, well, that's not really concept subsumption, but this works again because this here is the more specialized or more constrained version of the template, of the constrained function template. And this is chosen when we put in our test struct, which has both of these functions. And this overload is then chosen. And we get hello from B. And again, if we comment out the get special function, we will wait for the compiler. and we get an hello from A, which is really similar to the first example. And last but not least here, maybe you want to try out the same things we have seen on the examples before, but we don't want to try it out with named concepts. We want to try it out with, for example, type traits. So I have a print function which checks via requires clause whether T is of type double, but it doesn't use the same as concept. It uses the is same v type trait. This is perfectly legal for a requires clause. We can do that. And on the second overload in the function template here, we also check with the is same v template if T is a double, and we check whether the non-type template parameter n, which is an int, is bigger than 1. It's also perfectly legal to do that. And now if we call our print function with a double and a 10 as a non-type template parameter, compilation will halt and we get an error call of overloaded print function is ambiguous. Because again, all the stuff I mentioned before only works with named concepts. Here again, we don't have a named concept. We only have type traits and like const expr or compile time check whether a non-type template parameter has some certain value. And therefore, all these cool mechanisms I have shown for concepts like subsumption and looking at the most constrained overload won't work anymore. I have to get back to full screen. This is not full screen. This is full screen. And I'm sorry, I have to fix something here. My browser kind of broke. I'm really sorry. Now it should work again. So, and because it's so important, I want to look a little bit more at overload resolution with concepts. We've looked at it with our own concepts where we have our own requires expression and requires sequence. But now let's have a look at the same problem if we would be using concepts from the standard library. So we have three functions here. We have a print function which gets a template parameter callable and arg, and this is a completely unconstrained function template. And then we have the same function template, but we have a requires clause here, which checks via std invocable that callable is an invocable which can be called with arg. And in the middle, we have a third overload, which checks whether this print function is a predicate. So, so this means that callable can be called with arg and it returns something like a bool. And here, all the stuff we've learned before with the subsumption of concepts also work. If we call this function template here with something which is a predicate, then this will be called because of these subsumption words, because a predicate is an invocable and something more. So it's a more, or the std predicate contains the fact that something is an invocable, but is a little bit more than that. And if we just call it with an invocable, which doesn't return a bool, but maybe some struct or whatever, then this function will be called in the end. And if we call it with something which isn't callable at all, it's not invocable, then this base case here will be called. And this is really cool about the concepts from the standard library, that they all have these rules for concept subsumption built into their design. And this is also a really good argument to use concepts from the standard library if the functionality you want to have is already in the standard library. But of course, you can fail with that as well. So here we have a function which has a function with two function template with two overloads. One checks if something is convertible to float, and the other checks if something is convertible to double. And this is, of course, are two constraints which are most often are fulfilled at the same time. There's no case of subsumption or anything else here at all, and this will just lead to compilation errors. So, but from looking at it, it makes no sense to have these two things at the same time. But you can get, of course, these call of overloaded ambiguous errors as well if you're using things from the standard library in a way which makes no sense. So the standard library does not protect, the standard library concepts don't protect you from doing something which makes no sense, of course. Yeah, and this would be the end of the chapter about concepts. And just to reiterate here what we've learned in the last 51 minutes. So concepts provide an easy-to-use functionality to constrain templates. Overload resolution mechanisms based on subsumption gives us a fine-grained control about overloads. And concepts from the standard library provide a well-designed hierarchy of concepts. As most people might know, non-type template parameters were fairly limited before C++20. You could use integral types in their enums, pointers, null pointer, yeah, but that's about it, not much more. And this has changed with C++20 a lot, and now we can use many things as non-type template parameters, and this gives us a lot more opportunities. So what can be used as non-type template parameters today? We can use floats and doubles as non-type template parameters with a little bit of gotchas, which we'll see in the next slide, or one of the next slides. We can use so-called structural types as non-type template parameters. And what are structural types? So if we look up the definitions, these are literal class types with public non-mutable members and base classes, and all types of members and base classes fulfill the same requirement. So public non-mutable members. And a literal class type has a const explorer, constructor, and destructor, which for non-type template parameters must apply to the case we are using it. So it can also have non-const explorer constructors, but if we don't use these non-const explorer constructors and only use the const explorer constructors for building NTTPs, then this is still fine. And which is really cool, as if we have lambdas without captures, we can also use these as non-type template parameters. Then let's have a look at how structural types look. So here have some examples of some structs, and we will now discuss whether we could use them as non-type template parameters or not. First example is an empty struct A. And this can be used as a non-type template parameter. It has no user-defined constructors. Everything is okay. The second example is the struct A. It has a const explorer default constructor, and it has a non-const explorer constructor, which takes an int. And interesting about this struct is it's either okay or not okay to use as a non-type template parameter. So if we use A as a non-type template parameter and have just the case where we use the default constructor, it's totally fine to use it. But if we have the case where A is constructed with an int, then it's not fine to be used as a non-type template parameter. Next example is struct A. It has just a const explorer constructor, so it's a user-defined default constructor, so this is totally fine to be used as a non-type template parameter. And second example on this slide, we have a struct. It has no user-defined constructor. This looks fine in the beginning, but then comes the gotcha. We have a private member, y, an int. And because of this private member, it's not okay to use a as a non-type template parameter. And this is the only thing I don't like about these new rules for non-type template parameters, because in my opinion, this could be and maybe also should be legal, but it's not. We cannot use things which have private members. I'm sorry for that. And the last example here would be this struct A. It's also not okay to be used as a non-type template parameter. From just looking at the constructor, it would be fine. We have a user-defined const_expr constructor, which takes an int, so no problems there. But we have a user-defined destructor, which is not const_expr, so this thing can also not be used as a non-type template parameter. Yeah. Now, if we let that thing in, and we come back to that later, but now we will first look at floats and doubles as non-type template parameters. So, and this is a really cool feature, and it has only one downside or gotcha, which can fall up onto our feet maybe. So floating point numbers are considered equivalent in non-type template parameter scenarios if the underlying representation is the same. So they need to have the exact same representation in bits. This is okay, you would think, but this can lead to problems if floating point mathematics is involved. So if we have a look at the code, here I have some examples. So code works as follows. We have a struct A, which takes a non-type template parameter double x, and it's an empty struct, so nothing special here. And now we construct several A's, and with this same as concept, we check whether two A's are of the same type. And we start really easy. We have a A of 1, and we check whether it's the same as A of 0.5 plus 0.5, and we do a static assert around it so that we get a hard error if it's not the same. And clearly, 1 is the same as 0.5 plus 0.5, so this works with floating point mass. It gives us the exact same floating point value in the end. Also, if we look here, 4 times 0.5 is exactly 2. This works. Or even a little bit more complicated, 22 times 0.25 is 5.5. This works. Or 5.5 is the same as 11 divided by 2, so all fine. And up until line 30, we would think, okay, no, Hendrik has been lying to us. There are no gotchas or problems with that. But things start to get bad in line 15. So I want to check whether A of 0.3 is the same as A of 0.1 plus A of 0.1 plus A of plus 0.1. But this isn't the same. Oh, this does not work, because in floating point mass, adding 3 times 0.1 is not exactly 0.3. So the underlying representation of the resulting float here is not the same as, double of this double here, it's not the same. So these types are not the same. So the same as will evaluate to false, and the static assert here will trigger. We can also achieve that with less calculations. We can take 1.2 and subtract 0.3. We expect to get 0.9. But again, these results are not exactly the same in the bits representation or the underlying representation, however you want to call it. So these A and these A are not the same type, and our static assert here is triggered. And maybe the most obvious example, so from a mathematical point of view, plus and minus 0 are the same thing. They are two entities in floating point math. And of course, because they are two different entities in floating point math, they don't have the exact same underlying representation, which means same as here will say this is false and our static assert is triggered. And this is totally okay. We need to know that if we're dealing with floats and doubles as non-type template parameters to don't shoot ourselves in the foot, basically. So before we have a look at the next new features, a quick reminder. So since C++ 17, we are allowed to use non-type template parameters with auto. So we can write template auto x. And this feature is really, really useful for C++ 20 if we want to pass lambdas as non-type template parameters. And we have a look at examples here. So how does this work? We have a template, class template struct, template auto func, and it's called thing, and it's a function get, which takes a value, and it returns the value by calling func of value and then returning this return value. And then we can go into our main function. We have a lambda here, which is called calculator. And what it does is it takes a double, it returns 2 times of the double. And now I can declare my thing with my template parameter calculator called the get function. And as we expect, I would get the value 10 here in return. And this could be an interesting feature if you have code where you have like complex mathematical logic, but parts of that needs to be exchanged. Yeah? I don't know. In my mind, I'm seeing a text calculation here with different rules from different years where maybe you want to put these things which change in the different years, maybe into a lambda, and the general calculation which stays the same is in the struct. Yeah? Could be, yeah, maybe you have better examples for that and can tell me them later. But I think this is a useful feature. But we can break it. And this function breaks easily. So just by glancing here at the code, it looks, I want to do 16. It looks fairly similar to the code we have before. So again, we have our template auto func, our struct thing, the get function, and we return func of value. This has stayed the same. And now here we have a value of 12 and our calculator lambda. And now we capture here val by copy. And then we cannot build thing of calculator again. We get the red squiggly lines and some compiler errors here. And why is that the case? So it tells us our lambda is not a structural type. And why is it not a structural type? Because the capture here is a private data member of the lambda. So now we have constructed a lambda which has a private data member. It's our captured val. And because private data members are not allowed for non-type template parameters, this code does not work. And this is something I really don't like. Personally, I would love to be able to do that thing here. And I also think that this should be possible in the future. It should be made possible. Yeah? In my opinion, there is no reason that private data members should be forbidden for structural types, unless somebody disproves me on that. I'm open for discussion here, but I really, really, really hate that this is not possible. And I'm interested on hearing your opinion on that later on. So this concludes the lambda section. And in the end of the NTTP chapter, I want to show 2 examples or applications, as I called them, where I think this new non-type template parameters make sense in real world code. And you can already find these things in real world code if you look in GitHub, for example. So one thing is strong types. So as you might know, strong types is the idea, instead of having like a function which takes 5 doubles and returns 1, that we assign the function parameters meanings by wrapping them into a struct and giving the struct a useful name, like, for example, velocity or weight or I don't know, whatever you want. And usually if you look at libraries which do strong types, they do it with tags. So empty structs, which are only used for generating a distinct type. But with C++20, we can create a basic compile time string thingy and use this as NTTP for creating distinct strong types. I will show first from the old school example here. So how does this work here? So I have my struct strong type. It contains a value, which is a template parameter, and it contains an add function so that I can add these two things of this strong type. And I've also a second template parameter tag, which I just use to generate distinct types. And for example, for that here, I have a struct meter and a struct kilometer, which are empty. And I also have, because I love them, user-defined literals for creating strong types of meter and kilometer here. And with that functionality, I can declare 5 and 15 meters and add that together. And if I would make this here into a kilometer, this wouldn't compile anymore. So basic application of strong types, or maybe a units library. So as we might know it from, or this has been possible in C++ for a very, very long time. It is used by a lot of people. There are really cool strong types or units libraries out there. But how can we change that in C++20 with NTTP? And what I want to do is I want to get rid of this thing here. I want to get rid of also these empty structs here. This is what I don't want to have. And what I can do is I can go to here and have a non-type template parameter, which I call string literal, or the better name for that would be fixed string, because there was a C++ standard paper in the past which proposed this exact same thing. So a compile time string with the name fixed string. But for this example, I called it string literal, and I also only implemented parts of it. So maybe it's fair to not give it the same name as the thing which was proposed in the standards proposal. And with that thing, I have the same, basically the same code here. I have my value t, which is of type t. I have my add function here. But now the difference is here, if we look at the user-defined literals for meter and kilometer, I don't have to use a struct anymore. Here I can write meter and kilometer as a literal, as a string literal here. I should not say string. Yeah, I can write it as text here, basically, which is really cool. And the magic behind that is that we can write a structural type, which is called string literal, which only function here is to capture the text. We put it in here and store it as an array of characters. And this is possible because of this constructor here, which takes a reference to a car star array, to a car array, sorry. And this is then stored here in the array. And because the conversion here works, I can just write meter and kilometer here and use it as the same way as I've done before. Of course, this won't work. And this makes it also really easy to define new types of this. Because in the example I had before, I had an empty struct meter and an empty struct kilometer here as a tag, but I don't need that anymore. Yeah? I can come up with something completely new. I can write strong type, I don't know, euros. And I don't know, how to call it, money. And this works. Because I don't need to have an empty struct as a tag anymore. And this is something I find really, really cool. And there are also some libraries around which already use this functionality. And the other application I find really, really cool, which is also useful more for units libraries, is stud ratio. Yeah? So you need some kind of ratio type if you work with units, if you have like prefix and prefix type, prefixes like kilo or yocto or whatever. And there is also already stud ratio, but this is designed as a type template parameter, and it uses template metaprogramming for operations. And with the new NTTP rules, we can do it differently just with const expr functions. If you want to see a cool library where this is already used, you can look at the MP units library from Mateusz Pusch, and he already uses this feature and has implemented it in there. And I will show you a brief example of that. So we start by looking at the classical way, which stud ratio works. So maybe I have some unit, which gets a type T, and I want to give it as a result of two stud ratio calculations. So I have my 2/3 ratio and my 1/6 ratio, and I want a base unit for my pseudo units library of the addition of that. So I use stud ratio add of 2/3 and 1/6 and put the result in here. And this works, but we can do better with the new NTTP functionality. What we can do is we can define a struct ratio, which contains the numerator and the denominator of the ratio, a constructor, and maybe a function which enables addition of two of these ratios. And with that, I can define a struct which takes this new ratio as a non-type template parameter. And what I can do now is I can define, again, a unit, which is the result of the addition of two ratios. And I don't have to use these aliases anymore, and I can just add them in a natural way. And this works because this struct here is a structural type. It is only public members. This only has a public constructor. And here we have the add function as a const expr friend. And this works out well. It needs a little way of a little helper for doing all this normalization of the ratios, but this is not important here for the point I want to make. The point I want to make is that this makes it really easy to bring stud ratio in as a non-type template parameter, which is really cool. And again, if you want to see a full-fledged real-world application of that, have a look at the MP units library, which is a really, really well-designed units library, and I love it. We come to the, I would say, last chapter of the talk, which would be templated lambdas. And yeah, what we got before since longer times, C++ 17, generic lambdas. Was it even older? I don't know. So we can use auto and lambdas, and this means that X and Y have their own independent type from one another. And sometimes this is what we want, and sometimes it's not what we want, and there's no easy way to have force here that x and y have the exact same type with that notation. We can maybe improve on that with concepts. So we've seen a lot of slides ago that we can use constrained auto. So we could say maybe our lambda here, x and y should be integral types. So we can use constrained auto and put that in here. And now both x and y need to be integral types. And this is maybe what we want, but they are still not forced, for example, to be of the exact same type. But with C++20, we get templated lambdas. So we can put here again a template parameter list. And instead of auto, we can then write type name T and then use T for the arguments. And with that, we can force, for example, X and Y to be of the same type. And this is also an interesting feature if we need the template, for example, because the second example here is we have a lambda which gets a vector, but we want to be generic on the type of the vector. And this is only possible in the exact same way here with templated lambdas. And of course, we can also use templated lambdas together with concepts. And what we can do here is we can put the usual requires clause here. So reading that maybe hurts your eyes a little bit. It hurts my eyes a little bit when seeing that, but it's possible to have your template parameter list, your function parameter list, and then a requires clause. Or we can also use the shorthand notation for putting the concept name instead of the type name keyword. And this works as well. Fewer places which require type name. So I don't want to dedicate a chapter to that, but I just want to remember. So in the past, we had to write type name a lot if we want to refer to something like a nested type of a template parameter, but this has gone away as well. And for example, we can have a look at an example there as well. This code from before. We could have something like template type name T struct A, and maybe we have something like this using new inner type equals T inner type. And with C++20, this is perfectly legal code. And with C++17, compilation fails. And this is really cool. This can be used in a lot of places. You can also do something like this, T in type X. Also works. Or use it as a return type of a method. So T something get value. So we can also have templated member functions. So template type name u equals the other thing. Second value. Maybe it returns u. Works as well. So just remember, in a lot of places where you need to write type name before, you don't have to anymore. And this is also really cool because, again, if I crank the compiler down here to C++17, the error message is just need type name, need type name, need type name, and oh wonder, need type name. So the error message tells us we need to write type name. Although the compiler knows that we need type name, it still forces us to print type name there, to write out type name there. And I think it's a wonderful thing that this has gone away with C++20.